Hey guys, today we're going to be going over the alkene hydrohalogenation reactions and the free radical alkene hydrohalogenation reactions. Alright, so to start, we're going to start with the alkene hydrohalogenation reactions. These are normally reacted with a HX molecule. The X represents an alkyl halide, so iodine, bromine, chlorine, all of those. The HX molecules are generally highly polar, which causes the X, I'll say in this case of bromine, the bromine will pull the electrons towards itself in the bond, making the hydrogen here a little bit more electrophilic. So in that case, when it's reacted with an alkene, the pi bond electrons on the alkene, they're very nucleophilic. They'll go and attack the hydrogen, since it's more electrophilic, and break the carbon-carbon bond, therefore getting us a carbocation. These reactions follow Markovnikov's rule, which states that the alkyl halide X will be going on the most substituted carbon. Since these also are, they form carbocations, and also there can be rearrangements, so a methyl or hydride shifts. Also, one of the big things for these is that there's a ring expansion, which is possible if it's a cycloalkane or alkene due to the carbocation on there. So I got a quick example here. This is an alkene, reacting with hydrochloric acid. As we can see here, that the chlorine is going to be pulling the electrons in that HCl bond towards closer towards itself. So the hydrogen will be a little bit more electrophilic, will be much more electrophilic. So those pi bond in the alkene can go ahead, the electrons there can go ahead and attack the hydrogen, putting it on the primary carbon right here. And then we get a carbocation on the secondary carbon because we're following Markovnikov's rule. But you notice that this secondary carbon is connected to a quaternary carbon with the two methyls. So one of the methyls can come down here and rearrange, doing a methyl shift with the secondary carbon, therefore moving the carbocation to the tertiary carbon. Now, since the chlorine will come in and do a nucleophilic attack onto the tertiary carbon, and then attaching itself to the molecule, resulting in us with this product here. So that is how a alkene hydrohalogenation reaction happens. All right, so now we're going to go ahead and talk about the alkene free radical hydrohalogenation reactions. They're somewhat similar to the hydrohalogenation reactions, the regular ones, but there's some big differences. So to start, generally these use peroxides or peroxy acids, the big key feature for these is that a radical will form in the reaction, and this is generally from the peroxy acid between the sigma bond of the single bond of the double oxygens. Once they react, the two oxygens will be competing for the two electrons in the sigma bond. So what will happen is it will split since they have the same electronegativity, and a electron will go to each oxygen, creating two RO radicals, R representing a carbon group. This also follows anti-Markovnikov rules. So the radical will be on the more substituted carbon, and say the alkyl halide or whatever will be on the less substituted. The reason why it will follow anti-Markovnikov is because the radical, the more substituted carbon a radical is on, the more stable it is. It's able to hold the stability better, similar to a carbocation. So I got a quick example here. So this is a cycloalkene reacting with HBr and a peroxy acid. So to start, the HBr will separate, and each one electron from this bond will go to the hydrogen and to the bromine, and then the oxygens will separate also, creating two RO groups with two radicals, since one electron is going to each group. So from there, we have the radicals floating around the solution. The hydrogen and the one OR group will go ahead and make a bond together with the two radicals. They have two electrons forming a bond, which is actually an alcohol. So from there, the bromine will then go ahead and react with the cycloalkene. The pi bond electrons from the cycloalkene will one electron will go and react with the radical the radical bromine, and then the other electron will go ahead and put itself onto, will create a radical here on the more substituted carbon, where the bromine will be on the secondary, as we can see here, and the radicals on the tertiary carbon, because it's more stable. So then another hydrobromic molecule will go ahead in the solution, will go ahead and react with this. So the bond, it will create will break again, and one electron will go and react with the radical here, forming the hydrogen right here. And then the other electron will go onto the bromine, causing another bromine radical, just kind of sitting in the solution. So we end up with the anti-Markovnikov, rules. We end up with the bromine on the less substituted and the hydrogen on the more substituted, which is where the radical was. So yeah, that's one of the big differences other than the radical, is that the regular hydrohalogenation reactions follow Markovnikov, and the free radical ones follow the anti-Markovnikov. Again, that is due to the radical. So. All right, so now we have some examples of both free radical and regular alkene hydrohalogenation reactions. As you can see, the substrate is both the same. It starts out as the same, and HBr is used in both, but one uses peroxide acid. So first, we're going to start with the regular hydrohalogenation. Since this hydrogen is more electrophilic due to the bromine pulling the electrons closer to each other, causes it to be more electrophilic. The pi bonds on the electrons for the alkene will go ahead and attack the hydrogen, taking it and putting it on the less substituted carbon, because this is following regular Markovnikov rules. So the carbocation will be on the tertiary carbon. The bromine will then come in as a nucleophile and attack the tertiary carbon, attaching itself to this, and this is our final product for this one. And then for the free radical version of this, we have first the HBr will split, so we'll get two radicals with the hydrogen and the bromine radicals, and then we'll get the oxygens who have the same electronegativity. We'll take in an electron on each side, and so we'll have two OR groups also. So then the OR group in the H, since the oxygen is not as happy being in a radical as, say, a bromine, so the oxygen will go and lash out and take the hydrogen, and so then that will form an alcohol. As you can see here, the formation of the alcohol is right there. Also, key note, remember to always, if you're using radicals, to always use a half arrow, because the half arrow represents one electron, compared to this full arrow here represents two electrons. So then we take the alkene, and the alkene will react with the radical bromine. The less substituted carbon part of the bond will go ahead and react, the pi bond will react with the bromine, causing the bromine to go onto the less substituted carbon here, and then the radical will go onto the more substituted carbon, because it's able to hold the more substituted carbon is able to hold the radical better. Then another HBr in the solution will come in, with this time without a peroxide, and then that will split again, just like how this did. So the bromine will become a radical, but this time the hydrogen will go ahead and form a bond with the radical here. Whoops, it seems I forgot to put an arrow here, so this will form a bond here and create the hydrogen on the more substituted carbon, replacing where the radical was. So our final product will be this, with the bromine on anti-Markovnikov rules. So the bromine's on the less substituted, hydrogen's on the more substituted carbon, and then a radical bromine sitting in the solution. So yeah, that's going to be it for today. I hope you guys all learned something from this, and thank you.